Afternoon to everyone from Singapore. My name is Ernest. I'm from the Department of Mechanical Engineering, National University of Singapore. Okay, today I'm going to present to you some recent developments in my group pertaining to cooling and dehumidification technologies. As you know, in this part of the world, particularly in Asia, right, air conditioning and dehumidification technology is a very key part of our lives. Without aircon, I think many of us would not be able to work as well as we will be able to do. Okay, let me start off with a new quotation that I found recently from Scientific America. It states that one of the greatest ironies of climate change is that as the planet warms, the technology that people use to stay cool will only make the climate hotter, right? So if you reflect on this particular quote from Scientific America, you realize that human beings are one of the key culprits in making our climate hotter as we enjoy the cool effect of air conditioning. So reflecting on this, we will have to ask ourselves the question, can we evolve the next generation of air conditioners that are less detrimental to our climate, right? So the answer is yes. Okay, so I will demonstrate to you how that has been accomplished within my research group. Okay, first start off with some of the challenges that we are facing. As you know, we are still presently using the vapor compression air conditioning, right? So that technology has been invented in 1902 by the gentleman called Willis Carriers. It's a bit more than a century-old technology. It uses a compressor, right, to compress the chemical refrigerant from a low temperature to a high temperature so that you can enjoy the cooling effect while rejecting heat to the environment. It uses a chemical refrigerant, either it's CFC or HCFC, and it has global warming environment issues coupled with this ozone depletion effect. So the other fact that we have to realize that this system actually does the two tasks together. That means it cools at the same time you remove the moisture from the air. So in other words, it does the sensible and latent cooling in one single process. And in terms of performance, right, the vapor compression cycle, the performance is about 3 to 4. This is what we call the coefficient of performance. COP stands for the coefficient of performance. The higher the value is, the more efficient your system is. So for example, Daikin and Mitsubishi's air conditioning system, which are well known in the world to be very efficient, they have a COP within this range, right? And this unit, as you enjoy the cold air inside your room, as you know, this will be the fan coil unit inside your room. You have the other component that is parked in your balcony. Okay, this is the part that is rejecting the heat to the environment. And the heat that's coming out can be more than 50 over degrees. So imagine your environment, for example, in Singapore, our typical outdoor weather is about 30 to 32 degrees. Well, this unit is rejecting heat about 50 degrees. You have a delta about 20 over degrees, constantly throwing to the environment, right? And this system is pressurized. The refrigerant and the heat exchanging tubes are all pressurized. So any leak to the environment, any cracks to the tube, the chemical refrigerant will leak to the environment. And it's a very noisy process because of the compression effect carried out by the compressor. So these are the key challenges we have to recognize on the current air conditioning systems that we are using. So in our group, we'll reflect this problem, right? And then we say, can we evolve something that is much more energy efficient and at the same time it doesn't reject that kind of heat to the environment? So we have dissected the problem and look at it. Can we carry out the two processes separately rather than a single process that does moisture removal and then cooling in one single process? So we look at it and then we realize that we can actually do that, right? So my group came out with a stage 1 process, which actually we use a membrane sheet technology to sieve out the moisture from the air, right? And then followed by using a water-based cooling system, which we call the dew point cooler, meaning that the water doesn't come in contact with the air, right? But using part of the dry air to vaporize the water in the adjacent channel so that it can cool the dry channel. That means you're using the water layer in the wet channel to cool the dry channel. And in that sense, we actually accomplish what we call the air conditioning effect, using the membrane to remove the moisture and using a dew point evaporating cooling system to do the cooling. And with that, if you look at this very simple animation, right, we have the membrane. The first stage of the hot and humid air goes through the membrane. The water will be sieved out, and then followed by the second stage, which we call the dew point evaporating cooler. Typically, we take about 15 to 20% of the air that's coming in, and we let it go to the wet channel, right? As the 15 to 20% of the air that goes through the wet channel, it vaporizes the water in the wet channel and cool the adjacent dry channel. So the air will proceed accordingly. So this channel, one stage of this system, the dry and wet channel, will be able to drop the temperature of the air by about 3 to 4 degrees. So if you desire maybe about 10 degrees of temperature drop from your air, then you need to repeat this process 3 times, right? So in other words, the air that is coming out from this entire system is both cool and dry, similar to what you get in your typical vapor compression air conditioning system, right? And with no compressors, no chemical refrigerant, we can reach very high COP, about 8 to 10. And that's very highly desirable. It's about 2-fold, much more energy efficiency compared to your current vapor compression system. So the membrane that we use is synthesized. You need to synthesize it. And then we have a metal mesh, right? We use a TiO2 ceramic membrane to layer the bottom of the wire mesh to fill up the gaps and also to lend it the strength that it needs. And then we layer the top layer with a highly hydrophilic polymetric material, right? So this highly polymetric material will absorb the moisture, right? Will attract the moisture, right, from the air to the membrane, right? And then sieve it through the holes, right? So what is the unique of this membrane? That there's negligible pressure drop, right? As the air goes through the membrane, there's little or no pressure drop, right? There's no temperature change, right? Unlike some of the desiccants that you use to remove the moisture from the air, as the moisture is being removed, it releases the sensible heat to the air, so the temperature of the air goes up. So but in membrane technology, membrane dehumidification technology, the temperature of the air does not change, right? So that is a very big plus point. And then there's no regeneration of the membrane required. You don't need to impart heat to the membrane to push out the water from the membrane again. So no heating is required. And there's a low to moderate energy consumption by virtue of the fact that you need to pull some vacuum difference between the moving stream and the adjacent stream, right? This vacuum difference is typically less than 1 bar, and there's no air contamination involved. So unique feature of a typical good membrane that we have done in the lab is that it has very high water vapor permeability and selectivity, right? It's very highly durable. It's very flexible. As you can see, it can bend easily. It's easily to scale up. You can scale up the size from a small sheet to a very big sheet. And it's very low cost. The material to make this membrane must be low cost so that you can go for mass production. In fact, the whole entire process is a pretty green manufacturing technique. So the membrane can also be evolved to other configurations, right? If you have a membrane sheet, you can stack it up to like a stack system, putting the membrane, many layers of membrane in a stack system, and then the air that goes through will sieve out. The more moisture that you want to sieve out, you can stack up more membrane in a more sheet layer. Or the membrane can be reconfigured and roll up to become hollow fiber, right? The good thing about hollow fiber is that you can actually increase the surface area interaction between the air and the membrane, so you can sieve out more moisture from the air. Okay, if you compare some of the values that we obtained from a recent membrane done in US, right? This is a ceramic membrane done by PNNL, right? PNNL is the Pacific National Northwest National Lab, and the membrane that we have done in our lab, you can see there's a big difference in terms of the capability of the membrane to sieve out the moisture, right? The water selection effect, right? You can sieve out a lot of the water molecules compared to some of the membranes that are made in the US. And this has very high water vapor permeability as well, right? You can see from this data that we have presented here. And with that, we could design the first prototype, right? That is a non-vapor compression system, doesn't use compressor, doesn't use a chemical refrigerant, and doesn't reject significant amount of heat to the environment. So the first stage of the air, the hot and humid air, will come from the entrance, right? The water vapor will be sieved out from the membrane module. The membrane module will sieve out the water vapor. So the air that comes out here is dry, but it's still hot, right? It's not cool yet, it's dry. And then it goes through the second stage, which is the dew point evaporative cooler, where you use 15% of the air to go through the wet channel to cool the air in the dry channel. So subsequently, the air that goes through the dew point evaporative cooler comes out will be both cool and dry. So the exit point of this cooling system or new generation of air conditioner is both cool and dry, right? But the advantage, again, we highlight, is more energy efficient. It doesn't use chemical refrigerant. It doesn't reject heat to the environment. The 15% that we mentioned earlier will be thrown out to the environment, but because it goes through the water layer, the air that comes out is typically the wet bulb temperature of the water or the air, right? Typically about 26 to 27 degrees, right? So from that, let's do there are some big reports that we have because of this very new starting point of the new generation of air conditioner, there's a lot of publicity that's going on this new technology. We can consume 40% less energy using this new technology. It's cheaper to manufacture because we don't have a lot of metallic heat exchanger. There's no compressor involved, and there's no other components like valves and so on, metallic valves. And the membrane can, in fact, also make water from the air. As the membrane sieve out the water vapor from the air, you can actually condense that and make water from the air. So, for example, if you run continuously the air conditioning unit, the new system for 20 hours, you can actually harvest about 10 to 15 liters of water from the air. So it's a dual system where you enjoy air conditioning, you also can make water from the air. Okay, so we have huge publicity, right, both in Singapore and around the region and also globally to say that we actually are evolving the new starting point of the new generation of air conditioning, right? As mentioned, the vapor compression system has been around to us since 1902, more than a century old. Nothing has changed. Now in 2000, and we actually evolved this technology in 2 years ago. 2018 was the new starting point for the new generation of air conditioning system to take place. So let's revisit and make just side-by-side comparison between the new system and the vapor compression system. It doesn't involve a compressor. It's chemical-free. It uses water as the only coolant. So water is very environmental friendly. It's actually from nature. Water is from nature, so you cannot get any more friendlier than such an air conditioning system. There's no heat rejection to the environment, right? The wet stream that's coming out is 27 degrees. It's the wet bulb temperature, so it's much cooler than your environment, right? So the previous system, the vapor compression system, your condensing unit, the one that you use, is actually rejecting heat about 50 or more degrees of hot air temperature. Whereas now we are rejecting 15% of a little bit of air, which is about 26 to 27 degrees, much more cooler, right? And we can actually decouple the system. If we can do cooling and we can do moisture removal separately, right? So in fact, by decoupling it, you actually can evolve two different separate technology. Energy efficient is much better, about 30 to 40% improvement. And it can double out as a water harvesting system. As you enjoy aircon, you produce water from the air. The system is non-pressurized, so there's no potential of any leak to the environment. And it's very quiet compared to the previous system because there's no compressor involved. So from that, we can actually separate out the two technology. For example, for certain technology that you want it to be very friendly, you want to remove the moisture from the air, you just want to cool the air, right? Then we can evolve the dew point evaporator cooler to just remove the heat from the air, right? We have seen in this typical diagram, we have just evolved the overhead cooling system using the dew point evaporator cooler for places like outdoor cooling, right? Where you don't want to consume a lot of electricity, but you want to cool the air by 5 to 6 degrees, right? Just to bring down the air temperature by 5 to 6 degrees, enjoy a bit of cooling, but without incurring a lot of electricity. It can also be used on the bus stops, right? Typical bus stops, and because of the fact that it doesn't have the dehumidification process, the whole process can be run with just a small blower, a small fan, right? And this fan can be operated using the PV panel, right? The solar PV panel, and you have actually free air conditioning from the air. The heat from the sun, the radiation from the sun will run the PV panel, provide electricity for the blower, right? And then the blower will push the air through the dew point evaporator cooler, and then you enjoy 5 to 6 degrees of cooler air. Right? So we have just tested that outdoor without the membrane, right? This is without the membrane. This system is without the membrane, just the dew point cooler. We can actually bring down the air by 5 to 6 degrees for outdoor cooling, right? Without the membrane. And for indoor, without the membrane, if already the air is pretty dry, right? Pretty cool and pretty dry for indoor, there's really aircon. You can bring down the temperature of the air even cooler to 18 to 20 degrees, right? If you desire much more cooler air for a certain part of your indoor environment. So we have made it into our platform as well for outdoor testing. We tested our system for outdoor using the membrane and the dew point evaporator cooler, and we tested it out in outdoor for one of the alfresco dining, right? Outdoor dining, and then we show that we can provide the cool and dry air to the patrons in the outdoor restaurant, right? And then they can enjoy the cool air, but very environmental friendly and very energy efficient, right? Without throwing hot air to the environment, right? And then reducing the energy consumption as well, right? So this has we have received very positive feedback from many people who came to look at the system and realized that this is in fact the new generation of air conditioning system that they are looking for. Right. So next in my presentation, I've talked another technology that we have worked very hard on is the super absorbent technology. This is a super absorbent technology that can remove huge amount of moisture from the air, right? And it's very important for dehumidification effect. So this material is a mixture, is a composite polymer and some other material, right? And then this material, if you compare with silica gel, right, which is very well known, silica gel is a well-known benchmarking for a desiccant, right? We can actually remove 4 times more moisture compared to silica gel, right? And a good thing that it requires very low temperature to regenerate. Silica gel typically require about 80 to 120 degrees type of heat to regenerate. Well, this new generation of super absorbent only require 40 to 50 degrees heat to push out the moisture, right? And it has very short regeneration time compared to your silica gel, and it has very reduced pressure drop. The good thing about this material is that you can coat on any metallic surface. For example, you can coat on the heat exchanger and make the heat exchanger active to remove the moisture from the air, right? As you know, most of the heat exchanger is just removing heat from the air. But by coating this material on a metallic heat exchanger, you can activate the heat exchanger to, besides removing the sensible heat, also remove the moisture from the air. And that is a very big plus because we can see a lot of application in this, right? And a lot of energy savings potential as well. So we have compared this material with some other material that has been reported in the literature, right? For example, a material that has been reported by MIT and Berkeley in science, right? And they call their material the ultra absorbent. We found that our super absorbent actually has much more absorption capacity, right? And much more superior than what they reported, right? And then we also can use this material to harvest water from the air, right? We compare to those material that are involved that are synthesized by the MIT group, right? So looking at this diagram is about 5 to 7 times more absorption capacity, right, compared to silica gel. And the other beneficial effect that I didn't mention is that this material has antibacterial, anti-germs, and anti-fungus effect. And that's very important, right? Particularly when you talk about air conditioning, you do not want your air just to be cool and dry, right? But you also want your air to be of a good hygiene quality. I mean, very environmental hygienic, right? The air that can be that doesn't produce indoor air quality problems, right? So this material has antibacterial, germs, and anti-fungus effect. So if we coat this material on the heat exchanger, right? Like I mentioned, it can activate the heat exchanger to become moisture absorption, absorb moisture from the air, besides cooling the air as well. So if you look at it, we can use it in what are the area of application that we can use this for? You can use this in a car engine, right? As you know, in a car engine, there's a lot of heat that's produced by the car engine, and we can use the car engine heat to push out the moisture from this from the heat exchanger. One is absorb the moisture when it's saturated, right? And the air that goes through this heat exchanger, besides being dry, it also being cooled. But the refrigerant that cools it no longer need to cool it at very low temperature, right? About 5 to 6 degrees. Now you can cool the air at about 15 or even 18 degrees C, right? The reason being that the chemical refrigerant previously need to be 5 at 6 degrees is that it need to condense the moisture from the air. By coating this material on the heat exchanger doesn't need to remove the moisture. It just need to sensibly cool the air. So in other words, it can operate at much higher temperature, about 15 to 18 degrees, right? Compared to previously 5 to 6 degrees. So the higher the temperature your cold refrigerant, your cold heat exchanger or your evaporator coil is, the more energy savings you can yield, right, from there. As you know, if you reduce the energy consumption for your car air conditioning, right, then your fuel that you previously used to provide, you need to convert it to electricity to run your air conditioning. There's more fuel for your car to travel, right? The mileage of the car can be much higher. So this is one of the big impact, right, from that perspective. Now let's look at a very large operation, right? Now, so you can say that, everything seems to be very small scale and everything, but how about for large scale operation? As you know, air conditioning is not just small scale, but we also look at very big systems. For example, your chiller room, your chiller plant systems, and so on. Those are operating at very big system, right? They don't run at small system. As you go even much bigger, you are talking about district cooling system. District cooling system, they use huge chiller, right, to run the chill water to your AHU or the air handling unit or your different building just to cool and dry the air before the air can be provided to your individual rooms and offices. Right? So what is the effect? Can we actually scale up all this technology and bring the effect to a much larger scale? Okay, the answer is yes. Right. So as you have mentioned previously, we have made very small membrane, right? But again, I did mention that we can actually scale up the membrane easily, right? So we actually scale up the membrane significantly much larger than that small little sheet that you have seen here, which I can handle with my hand, right? We have made membrane sheet about 1.5 to 1.5 meter, right? Many sheets of this, and we can stack up the membrane sheet to very deep heights. So for in this case, there are about 80 to 100 pieces of membrane all stack up like sandwiches, right? And we can confine them to a module, right? We can also have the heat exchanger that previously was very small, coat the material on a small heat exchanger. Now we can scale it up to very large size heat exchanger for big size air handling unit as well, right? So we can have technologies from very small system and scale it up big to have that big effect, right, on large building air conditioning system. So what is the benefit, right? For example, I need to highlight that if you can remove the moisture from the air for big systems, right? You can remove the moisture from the air at the air handling unit. In other words, your chill water that you previously provide in your air handling unit need to be about 5 to 6 degrees. Now you no longer need to operate at 5 to 6 degrees. You can provide chill water at much higher temperature, 15 to 18, right? Or even 20 degrees, right? Rather than 5 to 6 degrees. Because the chill water no longer need to condense the moisture from the air. Right? The chill water simply needs to cool the air to a comfortable level. The part about removing moisture of the air has already been taken over either by the membrane modules, right? By the membrane modules, right? Or by the coated heat exchanger, right? Depending on which one you prefer to use. So what is the impact? The impact, if you increase every degree you increase in your chill water temperature, right? Every degree you increase your chill water temperature, your chiller, your big chiller that you have in your building, they will enjoy about 4 to 6% increase in COP, or the coefficient performance of your chiller will increase by 4 to 6%, and that translates to about 3 to 4%, 3 to 5% increase in your overall chiller plant energy performance, right? So previously, if you are running about, for example, 5 to 6 degree, of providing 5 to 6 degree of chill water to your this plant, right? Your air handling unit room. Now you are providing it at about let's say 15 to 16, right? We ballpark it to 15 to 16. That is a temperature difference delta about 10 degrees, right? You multiply that by 3%. Let's be conservative. You multiply about 3%. Easily, you can realize about 30% energy savings, right? Using just this kind of new technology that we can put it into the AHU room to condense, to remove the moisture from the air, right? So that is how impactful that it can be. Okay, in Singapore, we are slowly evolving, looking at cooling townships, right? Estates and townships in clusters. In other words, we are looking at the introduction of more and more district cooling system, right, in Singapore. The reason why they are looking at this in this direction is because we know that cooling system enjoy what we call the economic of scale, right? The larger your cooling system, the larger your chiller, the potential of energy saving is much more greater, right? So because of that, we are looking at district cooling at much bigger level. Already we have 2 big district cooling plants in Singapore serving the industrial parks and the commercial and commercial buildings, right? But we are slowly even looking at district cooling even for residential areas, right? Residential buildings and areas where the users are just basic residents of the apartment, right? So the impact of this is that if we can distribute the water, right, previously at 5 to 6 degree to all the clusters of the buildings, right, clusters of building through the district cooling system, instead of 5 to 6 degree previously, because we do not have the luxury of the dehumidification technology like the membrane or the super absorbent, now we can do that at a different temperature, right? The chill water can now be distributed at 15 to 18 degrees, no longer need to be 5 to 6 degrees. If we can have all this membrane technology or the super absorbent technology introduced at all the individual air handling unit, right? So the chill water can now be provided at much higher temperature because they no longer need to remove the moisture from the air or condense the moisture from the air. That duty has already been taken care of by the membrane or the super absorbent, right? In other words, you are going to realize big amount of energy savings from that, right? Your power plant and so on that is used to run your district cooling plants no longer need to consume so much electricity, right? So that is a very, very big impact, right? From the point of view of what we say to be the new paradigm in cooling, right? For large scale and small scale cooling as well. Okay, so if you imagine the entire of Singapore, this is a typical map of Singapore. The whole entire map of Singapore is run by district cool, right? In other words, we no longer need to have split small unit air conditioner like you see. Everybody is enjoying district cooling, right? And at a very energy efficient manner, right? Because we have membrane technology, we have super absorbent technology, we have the dew point evaporative cooling technology to do all the cooling, to do all the dehumidification and pre-cooling that's required. So if we can imagine, if we typically district cooling are the pipes of the district cooling that carrying the chill water are all buried underground, right? And these pipes, they need to be heavily insulated by virtue of the fact that the chill water is running at 5 to 6 degrees and the outdoor temperature, for example, is about 30 degrees. So there's a big difference in temperature, and that's why you need your pipe to be heavily insulated. There's a lot of cost involved to insulate your pipe, right? To make it thick so that there's no heat losses from your chill water. That is previously when it was operating at 5 to 6 degrees. Now, with this new paradigm change or this game-changing technology that we introduced, either the membrane or the super absorbent at your air handling unit, the chill water temperature can now run at about 15 to 18 degrees, right? Not at 5 degrees. So in other words, 15 to 18 degrees compared to previously 5 to 6, your insulation of your pipe no longer need to be so thick and so bulky, right? It can be much thinner insulation that's required at your chill water pipe, right? But it's running for hundreds and hundreds of kilometers, and that will save you a lot of energy, save you a lot of besides energy, but also heat losses pertaining to energy, but also the costs as well, right? The cost to insulate the chill water pipes, right? So that is another very big plus, right? Both operational costs in terms of energy saving, as well as a capital cost in terms of using less material for insulation. Okay, so with that, I will end my presentation here, right? This is my email. You can contact me by my email. If you want more details regarding some of the more technical details of the technologies that I've introduced here, you can look at some of my papers that I've published, right? You can Google my name and check out my Google Scholar, right? A lot of the papers have very highly cited. I have more than about 10,000 over citations for my research paper publication, right? So you can take a look, and I'm more than welcome you to interact with me by email, right? And then we can discuss any potential collaboration opportunity. So with that, I will end my presentation here.